Hello everybody, welcome to this video on pricing and revenue management. In the previous video, I introduced you to the idea of variable pricing and how it can be used as a lever uh, with revenue management to increase supply chain profits. In this video, we'll be looking at, well, how do you manage a demand profile where you have multiple segments in it? So you have different segments which have different demand profiles. Would you be able to use variable pricing and revenue management to increase your profits? And if you were to do that, how would that happen? So that's the idea for this video. So to do this, let's take an example, and we will talk through this idea, and we'll talk through this model based on that example. So let's say that there is a trucking company. So To From is a trucking company that has purchased 6 trucks with a total capacity of 6,000 cubic feet to transport materials between Chicago and St. Louis. So they have some costs which add up to totally $9,000 per month. In market research has indicated that the demand curve for this route and for the tracking capacity is 10,000 minus 2,000 P. What does this mean? This means that if the price that you set is $2 per cubic foot, where P is the price per transport price per cubic foot. So if you set the price at $2 per cubic foot, then your demand is going to be 10,000 minus 2,000 times 2, which is 4,000. So demand will be 6,000 cubic feet. And the total revenue will be 12,000 because it's $2 per cubic foot. So 6,000 times 2. So it's $2 per cubic foot. So one thing to realize here is that demand will be 6,000 exactly, and that's what your capacity is. You cannot satisfy demand of more than 6,000. So what this means is that if you set the price at $1, technically your demand will be 8,000 cubic feet, but you cannot satisfy all demand or all the 8,000 cubic foot demand. So it doesn't make sense for you to set your price at $1. The minimum price you should be setting it as is at $2, but then you will be using up all your capacity. But with that price of $2, the revenue will be 12,000. Because costs are 9,000, your total profit will be 3,000. Now, instead, if you set the price at $3.50 per cubic foot, your demand will be only 3,000 customers, or demand will be only for 3,000 cubic feet, even though customers are paying for more. So your revenue is decently high, it's 10,500, close to the 12,000 that you have, but you also have the $9,000 of cost, so your profit is only $1,500. Now, here are you're offering two different prices to two different customers. When does that make sense? Now, if the question that the To From should be answering is, can you separate these two demand profiles? Can you have multiple customer segments? If you can, then you can offer them different prices. But if you cannot offer them different prices. So how do we know that we have customers who have different demand profiles? Well, it could be based on experience with things like, say, you have customers who have signed long-term contracts with you, in which case you might have a price that you've already set for them, right? Or you might have customers who book from you regularly, as opposed to others who might book from you once in a while, or there might be a new customer who might be just booking from you just once. So you might have different types of customers who come to your trucking company, in which case you offer different prices to them because they are different demand profiles. The demand for customers who book from you regularly is going to be a continuous standard demand. Demand from customers who don't book from you regularly is going to be a different profile, so you can offer them a different price. So in theory, a concept of differential pricing does increase total profits for a firm. So if you offer different demand profiles for this, that is, you say that I have two separate customers, some of them who will book 3,000 units of this at a certain price, and other customers will book 3,000 of it at a different price. You'll notice that our overall revenue will increase from 12,500 to 16,500, where you have some of your customers have booked it at $2 for the $2 per cubic foot. Some other customers have booked from you for $3.50 per cubic foot. in which case our total revenue will be 16,500. Why is that? Because 3,000 cubic feet have been sold at $3.50, and 3,000 cubic feet have been sold at $2. So for some customers, you're charging $2, half the price, and the other half is paying 350. So your total revenue will now increase to 16,500, and your profit has also gone up significantly, right? So variable pricing is definitely useful, right? So that's the bottom line that you get from this. So the question is, how does a company decide this? And that's what we're going to be talking about with this model, right? So let's look at how you do pricing for multiple segments. So one of the crucial things about pricing to multiple segments is that each segment will have its own demand curve, right? So demand for a particular segment will vary based upon the price that you have. So if all the segments have the same demand curve, then you basically do not have different segments. You have a single segment. So the way you differentiate different segments is by having different demand curves, right? So each segment will have its own demand curve. So how does the supplier maximize its profit? So if demand is DI, the difference between revenue and cost times the demand. So price minus the cost. So C is the cost to you. So $9,000 that you're being charged. So whatever price you sell it at minus C, so times the demand that you have, this is what determines the total profit that you make. And if there are no, so when you do revenue management, there are two types of revenue management you can do. One is where you assume that there are no capacity constraints at all. And in another case, you assume that there are capacity constraints. In this problem, in this particular example with the trucking company, there are capacity constraints, right? You have 6,000 cubic foot of capacity. You cannot you cannot rent out more than 6,000 cubic foot of trucking space. So that's the maximum that you have there. But if you're designing this from scratch and trying to figure out how much capacity to have, then you might want to begin with an assumption that we have potentially infinite capacity available. Then based upon the demand curves and everything, we might come to a certain understanding of saying that, okay, this is how much capacity we might need, right? So that's something that you can potentially do. So assuming that there is no capacity constraints, then if you look at this this formula here and trying to figure out what is the best price that I can offer, right? What is the optimal price that I can offer so that it maximizes my total profit? Well, because you're not assuming any capacity constraint, each segment can be maximized individually because the price of one segment does not affect the price of another segment. So you can optimize them individually. And to optimize this, it's pretty straightforward. Pi is the variable. Everything else is a constant. So you can just take the derivative of this, set it equal to 0, and find the value of P that maximizes this for us. And that's basically what you get here. So the price at which your profit gets maximized, assuming no capacity constraints, is AI over 2 times BI plus C over 2, where C is the cost per cubic foot. Now, the one thing I said before that is wrong is I said that there is a $9,000 cost and C is a $9,000 cost. That's not true. 9,000 is a fixed cost for the whole thing. C is a variable cost that depends upon the number of cubic feet you rent out. So it's a variable cost and not the fixed cost. Just keep that in mind. Fixed cost does not have any effect on the maximization process because it's a fixed number. Let's say that there's a fixed cost, you subtract a fixed cost K from this. When you take the derivative, the constant goes away. So fixed numbers don't actually make any impact on the way you calculate optimal prices. So that's the optimal price that you have here. But if you do have a capacity constraint, you have to write that capacity constraint. And the way we are going to solve this is we are going to solve this using the solver tool in Excel, right? So once you have a capacity constraint, it becomes much more complicated problem. But without capacity constraint, it is actually a very, very simple, straightforward sort of problem. So let's look at an example, right? So here is an example from the textbook. So a contract manufacturer has identified two customer segments for its production capacity. One is willing to place an order more than a week in advance, and another and the other that is willing to pay a higher price as long as it can provide less than 1 week's notice in production. So people who want to order and get their products right away, they're willing to pay more. The others are not. They are willing to give you a week's time to finish the manufacturing that you need to do. So customers that are unwilling to commit in advance are less price sensitive and have a demand production curve that looks like this. So they're less price sensitive, which means that they are okay with paying higher prices. But customers who are willing to wait for a long time, they are less price sensitive, so they are willing to pay more. So customers willing to commit in advance are more price sensitive and have a demand curve of 5,000 minus 40 times the price. So this is the demand curve for customers who want the product almost immediately. These are customers who are willing to wait for more than a week. Now, let's assume that the production cost is $10 per unit. The question is, what price should the contract manufacturer charge each of the segments to maximize its profit? So first, let's solve this problem assuming that there are no capacity constraints, and then we'll assume that there is a capacity constraint of 4,000, and then we'll see how this problem changes, right? So first, with no capacity constraints, the formula is pretty straightforward. So we use this formula here. So these are the two willing customers who are unwilling to commit and customers who are willing to commit. So with that, the optimal price is $130. So it's this is A, this is B, right? So remember, when we wrote this formula, it's A minus B times the price. That's the way you write the demand curve for the segment. So with the demand curve for this segment, the value of A is 5,000. So it's A over 2 times B. So remember, the formula is A over 2 times B plus C over 2. That's the price. So that's A over 2 times B, 5,000 over 2 times 20 plus C over 2. This adds up to $130. For the second segment, the price is $67.50. So essentially almost half, but slightly less than half. Right? Okay, so with that, you can, once you have the price, you can calculate demand. So if price is 130, I can plug in 130 here and find that demand is 2,400, and then I plug in 6750 into the second one, and I find the demand is 2,300, almost equally balanced. And what is the total profit? So total profit is 130 times 2,400 plus 67.5 times 2,300 minus right. So this is the formula for the total profit. So remember that you have to subtract the price, obviously. So this is the total revenue and minus the total cost. So all the 4,700 units that you manufacture, 2,400 for the first segment, 100 and 2,300 for the second segment, they all have to cost you $10, right? So our profit is going to be $420,250. But here we are assuming that we are able to manufacture all 4,700 units. And so this is a good example of where if you were going to plan this out, if you're going to figure out what your capacity should be, then you'd say that 4,700 is the capacity that you should be planning for, right? Or maybe 5,000, slightly more than 4,700. You just keep that on hand, so you have enough to satisfy all demand to maximize your profit, right? So by doing more, you will actually make less money, and the reason for that is if you make more units, then you're trying to sell them all, then you'll have to sell them at a lower price. Otherwise, you will not be able to sell all of them, right? If you're selling them at a lower price, your revenue is going to be lower, and so that's the case. So what this is telling you is that the best thing that you can do is price your one segment at 130, the other segment at 6750, and sell 4,700 units in total, right? And your total profit will be 420,250, and that's the best that you can do. Now, going back to the problem, what if we have a capacity of 4,000 only? What if we can only sell 4,000 units? Then what do we do? So if we can only sell 4,000 units, then we will have to we will have to use the Excel solver to solve this problem, right? So now here is another nice way of comparing what's going to happen is, let's say that you priced both segments at the same price, right? So let's say that we have this exact same price for both segments, and we do that. So 20 times P, it's the exact same price. So you can write a new profit function. And now if you optimize this, it'll be 10,000 over 2 times 60 plus 10 over 2. So the optimal price will be $88.33. That's how much you should charge both your groups, both your segments. And now you'll notice that the total profit is much lower than the $420,250 that you can make. So pricing them at the same price, you are definitely losing out on a good $32,000 in money, right? So now, if you have a maximum production capacity of 4,000, there are no simple formulas to do this. We will have to set this up in Excel, and we can solve this using Excel. And well, let's do that right now. I'm going to open up Excel. Okay, so let this set this up. So first things first, let's set up a place for our production capacity. All right, let me make this smaller. There. Right, so production capacity for us is 4,000 units. Maybe you can put it on there like that. Okay, right, so production capacity is 4,000 units. So we have a multiple segment. So let's say segment. So you have segment 1 and segment 2 with the corresponding demand values. So you have demand and the potential profit that you're going to make. So segment 1 and segment 2. For segment 1, let's say that this is, I'm sorry, I forgot to have. Okay, I'm going to say price. So whatever our price is, so demand will be 5,000 minus 20 times whatever our price is. And here it's going to be 5,000 minus 40 times whatever our price is going to be, right? And our profit will be whatever price we have times demand. And be profit again. Once I can just copy this formula down, right? So that's pretty much it. Now, a few things that we can do. One is total demand. We can have total sum of all demand, right? And total profit, obviously. So you can have the totals here, total demand and total profit. So this is the idea here. So total demand represents how many units you can sell, and we have a capacity of 4,000. So that's something to keep in mind. And these are the two values, price. So this is the price. So I don't need my formulas anymore. So let's just moving a few things aside just so that okay, so these are the two price values, and that's what we need to decide. So that's the value that we're trying to figure out. So that's why these are the two variables that decide the whole problem. So these are our decision variables. And our objective is to maximize our profit. So this is the total profit of everything. And so what we do is we go to the solver tool, right? Data solver. So our objective is to maximize. So remember that total the profit is here for me in say E6. So maximize the profit in E6. The changing variable cells, we are changing the values of the price. So the price is the only variable here. Once you set the price, demand gets set and everything gets set, but it's based on the price initially. And then I'm going to change that to LP because it's linear. Now, actually, I'm going to leave it at non-linear. That's fine. So we're going to add a constraint. So there's only one constraint here. The one constraint here is the total profit that you have. The total demand that you have has to be less than 4,000, right? So it can be less than 4,000 or it can be equal to 4,000. Very likely it's going to end up being equal to 4,000. You use up the total capacity that you have. So the total demand that you have, it cannot be more than 4,000 because that's a maximum that you can entertain. So with this, I'm going to click on solve and let's see what the answer turns out to be. So this is the same answer that we got, the 420,075. So it's slightly more or slightly less. That's okay. Now, one thing you'll notice here is that demand from one segment is 2166, demand from the other segment is 1833. And so that is why you set the price this way. So one thing that you can do, potentially do is add another constraint. Now this is tricky sometimes because Excel doesn't like these kinds of constraints, but you can add another constraint which says that these two have to be integers. I think you should be able to add that. No. Yeah, Excel doesn't like that. So that's okay. That is fine. Now, demand is 2166, demand is 1833. If you want to set them aside, if you want to make them 2166 and 2167 and 1833 to do actual calculation, so you could do that. But so this is the value that you got from the solver, but that doesn't mean that you have to use this exactly as it is. But keeping the optimal values, you'll notice that. So these are both price values. We'll make them dollar values, and these are all dollar values. So let's make them dollar values. And there you go. That's our optimal profit, $452,083, right? So that's the optimal profit that you end up with. Oh, right. I'm so sorry. I am so sorry. Profit, I did not include, I did not include the cost values, right? I just wrote demand times price. I did not include the $10 cost that we incur. So let me say, so I can write that here, minus $10 times demand. So maybe I'll just write it here in the overall profit. So let's say minus 10 times the 4,000. So 412,083. Now, it's not going to, again, so when you remember when I wrote this profit, I just said 10,000 times the 10 times the 4,000. So this is technically not going to have an effect on the actual solution that we have here. But in case you are not sure, you can always go back. Now that I've changed the formula, you can go back to the solver. You can go back to solver. Everything is the same. So objective is E6. So everything is the same. Just can click on solve. There you go. The solution remains the same because that was a constant. So constants don't have effect on anything. So $412.83. So that's the total profit that you have. So you will notice, so the couple of things that I want you to notice. One is that this overall profit is less than the profit that you got when you were assuming that there were no constraints. The total was 420,250, which is definitely more than the 413,000 that you get when you have constraints. So this is something you should realize. Whenever you have constraints always lower your profits. So if you're able to plan this in such a way with these two segments, you say that 4,700 is what my demand should be optimally, then you should plan for 4,700. You will make that extra $8,000 in profit. Otherwise, if you already have this demand, if you already have this constraint and you have to work within the constraint, the maximum profit that you can make is $412,083.33. And that's pretty much it, right? Okay, so I'm going to end this video here. It's already gone on for almost 25 minutes. I'll see you all in the next video, all right? Take care.